Hey everyone, I'm Jan Benhelm, and together with Sadik Hafizovic, we would like to give you a quick overview over the Zurich Instruments quantum computing control system, how we help our customer speeding up their developments, linking their qubits to quantum algorithms and applications, also report on the latest developments on the hardware and software side, essential to scaling up to 100 qubits and more. Let's get right into it. Sadik, please.
Thank you, Jan. We began our quantum journey roughly in 2014 when we realized that there's a big overlap of what we do at Zurich Instruments and with what quantum computing research requires. At about that time, we decided to grow our mission to include that we want to help build the quantum computer and that we want to become the world's leading supplier for quantum computing control systems. We began by adding an arbitrary waveform generator for qubit control, then a quantum analyzer for readout of the qubits, so that by 2018 we had our first generation quantum computing control system on the market, as is shown here on that slide. The focus was clearly on superconducting and on spin qubits, and on today's noisy intermediate scale quantum systems. So when you look at the quantum computer, what is our role? You can look at the quantum computer as a functional layer stack where on top you have the application where the value is generated, where the chemist is developing his new proteins, where the pharmacist is developing new drugs. In logistics, routing is done, and in finance, portfolios are optimized. On the bottom of that stack, you have the magic, the physics package, in our case, usually superconducting and spin qubits. Now, we are in between those layers. We connect the physics, the qubits, to the software layers in the stack. And we do this in a way that is compatible to different software layers, so that all the different applications can reach through us to the qubits. Let's have a look on what that takes in a bit more detail. There's qubit control. We have our high-density arbitrary waveform generator that works in the baseband. It generates the flux pulses for tuning the superconducting qubits. It also generates the control pulses, which can be upconverted using our HDIQ upconverter. Then there's a component for qubit readout, that is our quantum analyzer. It can read out up to 10 qubits frequency multiplexed on a single line, and it does so in a very fast way. It can do it within coherence time so that the result can be used for either active qubit reset or quantum error correction. Then, very important, we have a system control unit, our programmable quantum system controller, that takes care of the synchronization of all the components in the electronics stack, and also it has global knowledge of all the readout results. So we can do syndrome decoding up in the PQC in real time, in coherence time, and then distribute the results back to the control units in order to take action within coherence time. And last but not least, there's a lot of software. We have our Lab 1 user interface that allows complete control of all the components and various APIs, Python, C, piked, so that the system can be controlled to the full extent. So with this system available since 2018, we have clocked up a track record that I'm very happy to share. Here's a little overview of the success stories of the recent time. And I'd like to point out, for example, the Surface 7 implementation, where the ETH Zurich was the first to implement a surface code and super fast 4 nanosecond single qubit gate that IBM has implemented. And again, ETH with stabilization of qubits. And we also have a very nice selection of bigger setups available. One is shown here on the right-hand side from the Quantum Device Lab. It's not their biggest setup, really nice lab there. Then at Berkeley Lab, we have the Advanced Quantum Testbed, where we have a beautiful system. Intel is doing their spin qubit research based on our electronics. And then there's two cases I want to go into a bit more detail because they are particularly nice. You can go to quantuminspire.com on the web and use a quantum computer through the web that will in the end run controlled by our instruments. And there's two different quantum computers available, one based on spin qubits, another one on superconducting qubits. And what was important in this project is that we deliver reliable instruments that are able to run 24/7. Downtime is nothing you want to have, at least not due to the control system. That should just work. Also, we could deliver a number of performance critical features that they didn't have to develop themselves, and thus by getting them tested from us, they could save time. The feature set is quantum specific, so that many quantum application specific things like calibration are supported by the system out of the box, and the system is ready to grow. We can grow as the quantum hardware grows to 100 qubits, for example. Very different case, but also very nice, is IQM. IQM is a startup company in Finland. IQM develops and markets quantum computers, the entire package, a quantum computer in a box. And Zurich Instruments, we supply the control electronics. You can see on the lower left on that slide, there's a image of what that quantum computer could look like. And in one of these cases, our control electronics would sit. Now here, the value proposition is a little different. For them, we reduce time to market and risk by integrating a control system that is known to work and function. Then reduced capital requirement. That for a startup really is an important point. And then they inherit from us the compatibility to the different quantum computing frameworks that are around. This could be Qiskit, this could be Q-Control, and that value adds directly to their own product. And also the roadmap is included again. We know how to get to 100 and to 200 qubits. IQM can focus fully on the quantum hardware, and they don't have, and the control system is taken care of. Speaking of roadmap, let's have a look at how we look at the roadmap at Zurich Instruments. We like to look at the roadmap in two thrusts. There's a scaling thrust, where the name of the game is to build bigger quantum computers with more qubits. And then there's the technology thrust, which is actually where the most work today is going on. The technology thrust works on systems of maybe up to 5 or 7 qubits. And the focus is on building better qubits, better gates, and developing new qubit technologies. We want to support both thrusts. We want to support everybody in both thrusts. We want to be in front of the curve here. And also what is important to us is that on both thrusts, the way of working, the user experience is similar, so that people can have the same user interface regardless on whether they're working on the technology thrust as on the scaling thrust, so that they can switch back and forth. And now I'd like to conclude my part and hand over to Jan, who will show us the recent innovations that have popped out of our roadmap. Jan, the floor is yours.
Thanks, Sadik. Let's start with some good news on the hardware side, and that is the introduction of the SHFOA, a super high frequency quantum analyzer, which we see as the second generation of instruments, mainly also because it includes the microwave generation and detection up to a frequency of 8.5 gigahertz. It's a very compact design. We offer a 2 and a 4 channel version, and with this you can detect up to 64 qubits. The SHFOA is fully integrated into our QCCS system, and we took great care also to improve the performance in terms of signal to noise and latency. Now, scaling up to larger and larger systems is both a technical but also an economic challenge. And it's very important that the price per qubit goes down, also the setup size, how many qubits you can have per instrument volume needs to increase, and the complexity on the control side needs to come down again. I think The introduction of the SHFOA is a significant step on all of these fronts, and I would like to invite you now to have a closer look on some of the new features and performance improvements. Let's start with the introduction of the multi-state discrimination. So the new instrument can detect not only 2 levels but up to 4 with different integration units, and that helps for qubit systems like superconducting qubits to control more levels and therefore improve the state initialization but also the gate performance. On the right here you see 30,000 measurements, very early measurements taken recently, where we discriminate between 3 states. We also improved the digital signal processing by introducing complex integration and digital mixing. The idea here is to lower the latency while increasing the fidelity, and to make some of the experimental steps no longer needed, and that helps to improve the efficiency of the workflows. Another important aspect considering the performance and to improve the detection fidelity is the purity of the spectrum. And I want to show you here on the right hand side comparison of the new technology with the widely available IQ mixing technology. And you see there's a much cleaner spectrum, a much higher spurious-free dynamic range achieved, so less components and components with lower amplitudes. Another important aspect here is the fact that these are much less prone to temperature changes. So we introduced a step of 10 degrees from 20 to 30 degrees Celsius, and you see a huge increase in spurious for the IQ mixing, whereas the situation for the new instrument is essentially stable, which makes calibration of any mixing no longer needed. How is this achieved? So the technology we apply here is called double super-heterodyne frequency conversion, and I want to quickly run you through how the signal input works here. So you would approach with a frequency of around 8 gigahertz, which would then be amplified and low-pass filtered with a 10 gigahertz filter, and then mixed with an intermediate frequency at 20 gigahertz. So you come down to 12 gigahertz, where you apply a narrow bandpass again that strips away all the spurious frequency component that you want to get rid of. And then there's another amplification mixing stage at 9 gigahertz. So you basically come to lie at around 3 gigahertz, where you amplify and filter again before the signal is then digitized in the first Nyquist zone of a 4 gigasample digitizer. And we already discussed the advantages with the IQ mixing scheme. We also considered the direct RF as a technology to use here, but with the present technology available and also with the requirements, which are actually quite similar to the ones from electrical frequency or spectrum analyzers, so wide bandwidth, linearity, and high signal purity. And that's why we chose to apply this electrical engineering approach known from spectrum analyzers to this physics problem. Now, how does the SHFOA integrate into larger setups? And we have this star-like topology here, which we chose because every time you add instruments, the performance of the entire system is actually not taking a penalty. And the system has 3 main different components. So first of all, there's the signal generation side, represented here by the HD AWGs with the blue edges, and then there's the quantum analyzer, so you can have one or many of those, and then you have a PQC or a central controller here, a programmable quantum system controller, and the current version can orchestrate up to 18 instruments. And the main job of this PQC is first of all to keep the whole setup in synchronization, to make sure all the instruments start at the same time when a new experiment is carried out. But the job is also to take back the qubit measurement results process them, and then redistribute the results of the calculations into the system. So every signal generator can then make conditional operations and branch the sequences, for instance, according to the algorithm. Now, how is all of this controlled? And the answer, of course, is by software. And here I want to introduce some new ideas we have. So up to now in generation 1, we left it basically to our customers to control the individual instruments and to bring them together into an entire system. And this is a complicated task, and there's different approaches to this task, which makes it also difficult to support. And so we decided to come up and extend our existing Lab 1 instrument control software with a part that we call Lab 1 QCCS software. So we added some additional components, which you see here in this blue box. And the idea is that people can map their experiments to the hardware, manage the execution, and then fetch and feedback the results back to the user through one single interface, a DSL, which is depicted up here. And this DSL is clean and well structured. So there is a part where you can define the setup, which is rather static. And then you have a part where you can define all the different signals, sections and pulses that will be used during real-time operation. And then there is a part where there is the timing introduced. So how does all these pulses and sections and so on play out? And then there is experiment execution and also the reporting back of the results down here. And I think you get the point. The development here is very much towards using the system as a single instrument. So also, let's say, a theoretical physicist should use the entire setup with full confidence without knowing much of the experimental details. So all the synchronization, real-time and near-time operation, and the trade-offs between the different parts are fully taken care of. We also expect some efficiency gains here through further automation and to having more things running in parallel than before. And the goal here is really to minimize the idle time of the system. And maybe looking a bit further into the future, we aim at the integration with higher layer software frameworks like Qiskit. And the goal here is that eventually people make use of a Zurich Instruments quantum computing control system and maybe not even realizing it. Now, more on the short term, we hope that our approach will lead to significant less work to our customers, speed up their developments, make better use of the resources, and then eventually help them to transition to larger systems. With that, I want to hand over back to Sadik for a quick wrap-up. Thank you.
Thank you. So what's the focus of our today's work to complete our second generation QCCS? We want to accelerate progress on the noisy intermediate scale quantum systems for 100 qubits and beyond. We believe it's really important to reduce system size, complexity, and price per qubit. We do so by integrating microwave generation and acquisition into our instruments, no more external IQ converters. We increase the channel density and we implement a strictly single instrument user experience. The user operates the entire QCCS as if it were a single instrument. We increase performance, which is particularly important when going to more qubits. Configuration and runtime has to be adequate for those bigger systems. Automation of routine tasks like calibration is also something that needs to be implemented on lower levels for performance reasons. Support for quantum error correction is key, maybe not the biggest challenge today, but it will come and the quantum computing control system will be ready for it. We add features. One strategy that we have here is we're open to different upper levels of the quantum stack. So we integrate the value that Qiskit and Q-Control, for example, generate into our control system. And we implement user access on both sample level, pulse level, and gate level. The user has the opportunity to choose. With this, I'd like to wrap up our presentation. At Zurich Instruments, everybody is really thrilled and excited to be part of this exciting journey, and we'd be more than happy for you to approach us with your questions and ideas. Thank you for your attention.